Okay, so just let me put it here for those that may be late. So no office hour today. Okay, so let us begin. So what we were discussing last time is we were saying that the PAC, or even agnostic PAC, learning criteria is in some way a little bit too demanding. It does not allow us to address many practical problems. We have to relax it. And the relaxation was this notion. So we had this relaxation of the notion of learnability, and we call it non-uniform learnability. Now, let me remind you what was the definition and in what sense this definition was different than the definition of usual learnability. So the definition is a class. So we are in exactly the same setting as before. We have a domain X. We are trying to predict some binary label, say 0, 1. And a class for us is a collection of functions from X to 0, 1, a collection of classifiers. So a class H is a non-uniformly learnable if there exists a function MH that goes from H times 0, 1 times 0, 1 to n, and a learning function A. A learning function is a function that takes labeled samples as input, a training sample as input, and outputs some predictor, such that for every probability distribution P over X cross our label set, every epsilon greater than 0, delta greater than 0, and every H in H if M is greater than MH of H epsilon delta, or greater or equal, then the probability when I take samples from P to the M, when I take M samples, that LP of A of S will be greater than LP of H plus epsilon is less than delta. So that I discussed this definition last time, but let me repeat the main points. So I think the main points to understand, first of all, is in what sense is it different than the definition of PAC learnability, and then what is the meaning of this definition. So in what sense is it different than the definition of learnability that we had before? The first difference is here. Before, we wanted a function that takes inputs just epsilon and delta. Now my function that tells me what should be the size of the sample is not only dependent on epsilon and delta, but I also allow it to be dependent on h. And then the conclusion is that if I get a large enough sample whose size may depend on h, then the error that my algorithm makes is not much more than the error that this h will make. In the PAC sense, we just had it, we had here, there was no h here. The sample size just depended on epsilon and delta. And we had this requirement for every h in h. Since the sample size did not depend on h, we had this requirement for every h in h. Now the requirement is for a specific h. So the intuition is that h, capital H, is non-uniformly learnable. You can think of it as a collection of experts, that I want to say that my algorithm is able to compete with each of the experts in this family of experts. So H is a family of experts, or family of classifying rules. And my algorithm is able to compete with each of them. It is just that my algorithm, in order to compete with a better expert, with a more sophisticated classifier, may require more examples. Are there any questions about this definition? Yes?
So here the variable is any given h, but for non-uniform learnability, we kind of break all the h's into like levels of different h's with different VC dimensionality.
But
I just wonder, like, is it that a whole lot of h's would generate the same mh if they all come from the same uppercase h class?
so we will see it in the next one. It is not that we cannot talk about the VC dimension of a particular h, right? Because for each particular h, no matter how complex it is, what is the VC dimension of a given h, of a given small h? If I give you only one, if I ask you just what is the VC dimension of a set that contains only one element, if the VC dimension of this is going to be always 0, regardless of how complicated h is. Because I have only one function, so this function cannot even shatter one point. In order to shatter one point, I need to have one function that will give it 0 and one function that will give it 1. And if I have only one function in my class, it cannot even shatter one point. So I cannot talk about the VC dimension of a particular h. I have to talk about the VC dimension of a class. And here I don't have a class. But intuitively, this is a good intuition, and we'll see it in the next theorem. OK, so far I just discussed the basic definition. What is the requirement? In what sense is it weaker than the previous requirement? It's still an interesting requirement because the strength of this requirement is that it holds, you see, the function here does not depend on the probability distribution P. So if you tell me how many, say that we are trying to do some kind of a prediction of the stock market, right? And you ask me, how much data do you need in order to tell me how well some stock will behave? So, of course, I cannot give you any guarantees because maybe tomorrow there'll suddenly be a big war with Russia and all the stock market will collapse, and it's not something that I seek for my data, right? But what I can tell you is I can predict this stock, its value tomorrow, as well as anybody in this class. So this class could be some powerhouse of experts. But here I tell you, it's not, I don't, rather than telling you with this number of examples I can compete with anybody in this collection, a big family of experts, I can tell you, it's not that I can give, with this number of examples I can compete with any expert in, I don't know what, Cornell University, but you tell me the expert, I look at his profile and tell you, oh, to compete with him I need so many examples. But it's still meaningful, because with so many examples, no matter what P will be, I will do at least as well as this capital, as this H. Okay? Now, let us see what does it give us. And the main thing is that this theorem that we have here that characterizes this non-uniform learnability. So it says that a class H is non-uniformly learnable if and only if I can represent it as a union of smaller classes. So if and only if there are classes H1, H2, so on, Hn for every n, such that we have two requirements. One, H is the union, n goes from 1 to infinity, of all those classes. And the second requirement is that for each n, the class Hn is agnostically Pak learnable. So a class is non-uniformly learnable if and only if I can present it as a union of classes that each of them is learnable in the old sense. So in that respect, it is similar to what you were asking about. So there are two questions that one can ask just seeing this theorem. First of all, does it give us something? Can we come up with a class that is non-uniformly learnable but is not learnable? Did it bias anything? So there are two questions here, two obvious preliminary questions to ask. One is there a class that is non-uniformly learnable but not agnostic, but not, say, Pak learnable? Does it bias anything new? Maybe I relaxed the definition, but it didn't give me any advantage. And the other natural question to ask is, this is asking, did the definition bias anything new? We can also ask, did the definition not go too far? Is there a class that is not non-uniformly learnable? Maybe the definition that I gave you now is so strong that it made everything learnable. But I think this should bother us less. Great, then we can learn everything. But this is, I mean, we want to know, did we gain anything? Because I already convinced you, or tried to convince you last time, that the definition of learnability that we had before was too demanding. Okay, so what about answering question number 1? So for question number 1, I just have to give you an example. And we can have many examples. So one example, I think I mentioned it last time, So one example is let in all our cases, in both our examples, let x be, say, just the real line. Now, in example 1, let H be the class of all threshold polynomial functions. So what do I mean by that? So so for each polynomial P, say A1, A0 plus A1x plus A2x squared, and so on, plus AD x to the d, let HP be just the sign, HP of x be the sign of this polynomial P of x. Right? So I can turn any polynomial into a predictor. I'll just take the sign of the polynomial evaluated at the point x. So here is a polynomial, and I can take its sign and turn it into a predictor of a 0, 1 labeled function. And now for my example, let H be the class of all such polynomial predictors. HP. So this is a very big class, because it turns out that I can approximate with this every predictor over the 0, 1 line. But it's a very big class, and I make here two claims. That, of course, first of all, I can represent H as a union of classes. So H is the union over n goes from 0 to infinity of classes Hn, where Hn is the class of all Hp, such that P is a polynomial of degree at most n. So H1 is the linear predictors. Linear predictors over the line are very boring. It's only just threshold functions. H2 is all quadratic polynomials. Right? So if I have H2 is the class, what do I get, for example, by H2? By H1, I get all polynomials of degree 1. So I take a polynomial that looks like P of x is ax plus b, and now I compare it to 0. So what will HP give me? How will this function HP of x look? It is the sign of P of x. This sign function will just be, for some time it will be 1, and then it will be -1. So this will just be one, h1 will just be one cut in the line. Because this is a monotonic function. As x, if I hit 0 and I keep increasing x, then I will not change my sign again. Right? And h2, when I allow quadratic polynomials, what will I get with the class h2? What will I get with the class h2? If I want to describe it geometrically, if I take a quadratic polynomial, I take a polynomial p of x is ax squared plus bx plus c, and I look at the function hp of x is the sine of p of x, how does it look like? I mean, geometrically on the line, where will be the zeros and ones, the minus 1 and 1s of this function? I mean, I know that the polynomial function, it looks like this, right? This is the function p of x. It's a quadratic function. So if I look at the sine function, it's going to be 1 here, minus 1 here, 1 here. So it's just a class of all either intervals or complements of intervals. For every quadratic function, either it looks like this, and the interval is a minus and the rest is a plus, or it looks like this, and the interval is a plus, and outside the interval it's a minus. So h1 gives me just threshold functions. h2 gives me all intervals and complements of intervals. What will I get from h3? h3? How will it look? If I take functions of degree 3 and take their sign, then I'm just going to have something like it is plus here, it is plus, oh, so it is plus, it is plus here and here, right? So it's a combination of an interval plus a threshold. And as I increase the degree, I will get more and more complex sets. Yes?
Is H1 a subset of H2?
Right, because H1 is a subset because I say P is a polynomial of degree at most n. But it doesn't really matter. You can define them either disjoint or that one of them is a superset of the other. Okay, so we are getting more and more functions, and what I claim is that first of all, so the class of all polynomials is just the union of all polynomials of degree n for every n. And then claim 2, each hn has a finite VC dimension, and hence is Pak learnable, or agnostic Pak learnable. So my conclusion is that H is non-uniformly learnable. But let us recall, what was I aiming for? What did I want to show you? What was I trying to show?
That H is not.
It's not Pak learnable. I wanted to show, right, so why is H not Pak learnable? Anybody has an idea? Yes?
Because it has infinite with dimension.
It has infinite with dimension. So here in another claim, H has infinite VC dimension. And I will not bother now to prove it. I'll just let it give you as an exercise that you just check yourself. I mean, each of you should be able to prove that this class has infinite VC dimension. Because for every, roughly, if I have a set of points that I want to shatter them, so you tell me which ones you want to be plus and minus. So you want these ones to be plus and this one to be minus and this plus and this minus. I can find some polynomial. If you don't bound the degree of the polynomial, I can find a polynomial that will be positive on your pluses and negative on your minuses for every finite set. So for every finite set and for every partition of this set into pluses and minuses, I can find a polynomial that will match this partition. And therefore, we can shatter every finite set, and it has an infinite VC dimension. So the other conclusion is that H is not Pak learnable. So we see that we got something new. We got now more flexibility than we had before. There are classes that are not non-uniformly learnable, but they are not learnable. And I mean, here I leave these two claims, two VC dimension claims to you as exercise to show that each Hn has a finite VC dimension and to show that the union does not have a finite VC dimension, has infinite VC dimension. A simpler but much less practical class, a simpler example, which I will not go into much detail. Let H be the set of all functions f from R to plus 1 minus 1 such that f minus 1 of 1 is finite. So I look at all the functions on the real line that give you only finitely many ones. Or in other words, so here is the real line. I pick finitely many points, and I look at the function that is minus everywhere, except for those finitely many points. That's how my function looks. It's minus 1 everywhere, and it's 1 only on finitely many points. And I claim for this set of functions, I just, again, leave it to you as an exercise, show that it is learnable in the non-uniform sense, but it is not learnable in the usual Pak sense. So here is the exercise for you. Again, it should be very easy, but good test that you are following what is happening here. Exercise, prove that H is non-uniformly learnable. That is, I can represent it as a union of Hns, each of which is learnable, but not Pak learnable. Okay, so you have a couple of exercises here just to make sure that you are up to what the course expects. Okay, did I answer the questions that I posed? What? Right, I didn't answer the question, the second one. Yeah. So I didn't answer the second question. The second question, is it the case that now everything is learnable? And here is the answer is no. It would not have been interesting otherwise. But I can say it a little bit more strongly. So here we have a lemma that I will give you as a, I'll not prove it here. I'll just leave it as a proof for the bonus of exercise of assignment 3. And it claims that for every infinite set X, the class of all 0, 1 valued functions over X cannot be covered by any union on n of Hn where each Hn has a finite VC dimension. So it is not non-uniformly learnable. The class of all functions, it's not non-uniformly learnable. It is still a non-trivial requirement to be non-uniformly learnable. But that will be, this is, I'll give you a hint in the assignment of how to do it. It's not easy. Just for reference, just remember that we didn't trivialize the notion of learnability. OK, so where do we go from now? So what I want to do is I want to do basically two things. I want to prove this theorem, and I want to give a basic algorithm for learning non-uniformly learnable classes. A basic, for learning PAC learnable classes, we had a basic, very simple paradigm. The paradigm was ERM. Now, how shall we learn non-uniformly learnable classes? ERM will not work because we know that ERM works only if you have a finite VC dimension. So we'll need something to replace ERM, a more sophisticated algorithm. So that's what we're going to do now. We're going to prove this theorem and present a more sophisticated algorithm that can learn such classes. OK? So we are progressing towards the, so the current goal is to prove the theorem characterizing non-uniform learnability. And the first step, I'll have here a kind of a halfway in between, a lemma that will say the following. Let us do one direction. If H is non-uniformly learnable, then there exist classes Hn satisfying these two conditions, such that one, H is the union of the Hns, and two, each Hn has a finite VC dimension, and therefore agnostic PAC learnable. So this lemma gives us one direction of the theorem, of the characterization theorem. The characterization theorem says you are non-uniformly learnable if and only if you can have such HNs. And now I'm showing you one direction. Okay, so what will be the proof? So you give me such H and you tell me it's non-uniformly learnable. I have to tell you how to cut it into slices, HNs, such that each of them will have a finite VC dimension. So what am I going to do? Given a non-uniformly learnable H, we know from the definition of non-uniform learnability that there exists some function mh of h epsilon delta, such that the requirements from this mh. I'm going to use this function to define the classes hn, to define how to slice h into smaller classes that each of them has a finite VC dimension. So I'm going to use this function that's guaranteed by the definition of non-uniform learnability of this h. So now define for every n, define a class hn. Hn is going to be the set of all h's in H, such that mh of h 1 over 8, 1 over 8 is at most n. So I have a class H. All I know about it is it is non-uniformly learnable. I don't know anything more than that. But the definition tells me if it's non-uniformly learnable, then I have this function mh. If I have this function mh, this definition makes sense. Now I have to show you that this stratification of H satisfies these two requirements. So now what I need to claim is that these Hn meet requirements 1 and 2 that we have here. Okay, so why do I meet requirement 1? Because this function gives me a natural number. For every h epsilon and delta, it will give me some number. So for every h in h, if I put here 1 over 8, 1 over 8, I'll get some number. So every h in h will be in one of those capital Hns. Right? So for requirement 1, it's very easy. For 1, given any h in h, let n be mh of this h 1 over 8, 1 over 8. So H belongs to Hn for this n. So it means that every H in H belongs to one of the classes. So the union covers H. What about requirement 2? How do I know that each of these classes has a finite VC dimension?
To show it's learnable.
What?
To show it's learnable.
I want to use the finite VC dimension to show that it's learnable. How do I know that this class has a finite VC dimension? Yes?
Because MH is bounded, so the VC dimension is bounded.
MH.
Bounded by
MH is never bounded, right? MH is a function of epsilon and delta.
Can we use the free lunch theorem?
Exactly. We will use the no free lunch theorem. The no free lunch theorem tells me that, right, assume I claim that for every n, so now what's the most elegant way of stating it clearly? Yes?
Sorry, I have a question. I thought the no free lunch theorem applied to the class of all possible functions.
Right. So I'll answer it here. Okay? So for every n, right, pick I claim that the VC dimension of the class Hn is at most 2n. And therefore, it's finite VC dimension. Why? Otherwise, if the VC dimension is more than 2n, pick a subset A subset of X, A of size greater than 2n, such that Hn shatters A. Right? This is our definition of VC dimension. If your VC dimension is greater than some number, then you have a such shattered set of a larger size. Now I'm going to use the no free lunch for all functions over A. Right? So now the NFL theorem tells us that we need more than n examples, n size, training sample to learn the class of all functions over A with precision, accuracy 1/8 and confidence 1/8. But since A is shattered by Hn, Hn contains all functions over A. So learning an Hn will be like learning all functions over A, and learning all functions over A require more than n sample size. However, we know that I can learn Hn with just n points. But, however, by the definition of Hn, it can be 1 over 8 learned from n size samples. Because the no-free lunch told us if you have a set and we want to learn all functions over this set, for epsilon equals 1 over 8, delta equals 1 over 8, I need to see at least half its points. So if we shatter a set of size bigger than 2n, at least half its point will be bigger than n, the sample size that I need. But the definition here told me that Hn is a class of functions that can be learned with just n many points when I fix my parameters to this epsilon and this delta. Okay? Yes?
What M is the no-free lunch theorem referring to in this example?
M for the no-free lunch theorem is this is the M in the no-free lunch theorem. We said if we have a domain of size M, and you have all functions over this domain, you will need at least M over too many examples. So if I shatter a set of size bigger than 2n, let's pick this be my M, and then I'll need at least M over 2 examples, which is n examples. Okay? Yes?
Why did you say that the MH is not bounded? Isn't it bounded by n?
Well, what does it mean bounded? I mean, if I allow here, you see MH is a function of epsilon and delta. So as epsilon and delta go down, MH goes to infinity. Okay? We talked about what is the value of this at 1 over 8, 1 over 8. That's always just a number. There's no issue here of being bounded or unbounded because I fixed epsilon and delta. You see, once I fix epsilon and delta, it is just a number. It's always bounded. If I don't fix epsilon and delta, it's never bounded. Because as epsilon goes to 0 and delta goes to 0, it will usually go to infinity. So although your intuition was right when you say MH is bounded, it's not a formal statement. Okay? So we showed one direction of the characterization. We showed that if you want to be non-uniformly learnable, you would rather be a union of finite VC classes. Now we need to show the other direction, which is this condition suffices. So now we need to show the positive direction of the characterization of NUL. So we have here another lemma, which will be a positive one, showing something is learnable. And it will say that if for every n, Hn is learnable, then H, which is defined as the union of all of them, is non-uniformly learnable. And the way we will show it, that we will assume by the fundamental theorem. So this is step 1. Each such Hn has the uniform convergence property. Remember, the fundamental theorem told us that being learnable is the same as having finite Fisher dimension, is the same as having the uniform convergence property. So what is the uniform convergence property? It means that for every, namely, for every Hn, there is a function. Let's call it Mn of epsilon delta. This is the uniform convergence function. What does it say? Such that for any epsilon delta greater than 0 and m greater than mn of uniform convergence epsilon delta, the probability as sampled by p to the n for every probability distribution p, the probability when I take such samples that Ls, that there exists an H in Hn such that Ls of H minus Lp of H is greater than epsilon, is less than delta. So I know I'm being very demanding because I'm invoking all kinds of technical definitions from the past. Okay, so let us just go over this definition quickly. Just to remind you, we talked about this definition. It says that the non-uniform learnability, the uniform convergence property, said that if I take a sample of this size, then this sample is epsilon representative. You remember there was a notion of epsilon representative? And epsilon representative meant that for every h, the empirical arrow was very close to the true arrow of this h. So this number, mn of epsilon delta, suffices to guarantee that our samples are epsilon representative. And epsilon representative means exactly this, that if you evaluate the loss with respect to the sample, it gets you an answer that's very close to the true loss of H. So this, in other words, this is just saying S is epsilon representative for Hn with respect to P. So this number was the sample size that I need, that with probability greater than 1 minus delta, my samples will be epsilon representative. So what are we going to do now? So where are we? We know that our class is a union of such classes. We know that those classes, since they are learnable, they have the uniform convergence property. So we have this function that guarantees uniform convergence. For every class Hn, we have this function Mn. And we need to construct a function M of 3 parameters, H, epsilon, delta, that will show that our class is uniformly learnable. If I'm losing you, then I'm afraid that I lost everybody. So what's unclear?
I guess I'm wondering why you can't directly use the agnostic pack M of class H sub n.
Yeah, it doesn't matter. I could use the agnostic pack number. I could use the... But the agnostic pack number talked about the existence of an algorithm. And I don't want to involve an algorithm here. Because you see, I cannot use infinitely many algorithms. For every class, I will have its own algorithm. The agnostic pack just said there exists an algorithm that can learn from so many examples. But then I'll get an algorithm for every class. And I'll have to combine them into one algorithm. So this is a more elegant, more clean way of doing it. The uniform convergence doesn't involve any algorithm. It just talks about these differences. Now, what is going to be the idea? The idea is that, so how to proceed? So the idea is that we are going to give every class with, now we add a new component to our discussion. And this is going to be a weighting function. Weighing or weighting? With T or without T? A function that assigns weights. Weighting function? OK. If you approve, then a weighting function. So what is a weighting function? It's a function W that goes from the natural numbers to 0, 1. And the idea is that Wn is the weight we assign to the class Hn. So every class will get a weight. And the weight is a kind of saying, how much do we... OK. Let me just make one more comment here before I explain what the weight is saying. And we will require that the sum over n goes from 1 to infinity of Wn is at most 1. Yes? What? You are right. Very good. Yeah, very good point. You get your bonus point. Right. So let me repeat what she was saying. What we have here in the bracket is the claim that H is not epsilon representative. It fails to estimate. The difference is bigger than epsilon. It is epsilon representative if it estimates correctly the loss of H. But this is the bad case. H is not epsilon representative because there is a big gap.
It's smaller than delta,
What?
but it's very unlikely for that to happen.
It is very unlikely for that to happen. Then the uniform convergence property told you that this bad case, that S is not representative, is very unlikely to happen. It has probability smaller than delta. But what we have in the bracket is the event that S is not epsilon representative. Okay, thank you. Okay, so we have this weight function. Now, our trick is going to be that, so we add this weight function, and we are going to use a reasoning which is called structural. The next idea, we have this weighting function, and we have this a principle, which is called structural risk minimization. What we are going to require so we give this weight Wn to every class Hn, and we can view this weight as a penalty. If we pick our H from this class, we are paying a penalty Wn. So classes that we think that they are likely to succeed, we'll give them a high weight. So okay. What we would like is, so the idea will be that given a sample, a training sample S, we wish to pick H in H that minimizes the loss with respect to S of H plus some penalty that grows as W of n shrinks for the minimal n to which for which H belongs to Hn. So we are going to say we have those classes. I have here H1, H2, H3, Hn, and so on. I get a sample. What I'm going to do is I'm going to see how well can I fit the sample. Of course, as I go to bigger and bigger h's, I will be able to fit the sample better. So if all I wanted to do was to minimize the loss, then I'll do empirical risk minimization and just pick an h that minimizes this. But now, on one hand, I want h to minimize this. But on the other hand, I want h to minimize the penalty. And the penalty grows as I go up in my classes. So on one hand, I'm trying to fit the data. But on the other hand, I'm paying a penalty for using an h that is coming from a high class. And by combining these two considerations, we can show that we can learn any such class. So the new idea is that we are going to have this weight function, and the weight function will determine a penalty for picking a too complicated h. So that's the basic idea. I will now turn it into a proof. OK, so let us turn it into a proof. We have our definition of the weight function, where weight function is any function that gives for any n a number, such that the sum of those numbers is at most 1. And now we are going to show that using this idea and a weight function, we can prove non-uniform learnability for these classes of unions, big unions of finite VC classes. OK, so here we have a theorem that will conclude our proof. So let H be a union over n goes from 1 to infinity of Hn, such that each Hn has the uniform convergence with a function m uniform convergence of n epsilon delta, and let W be any weighting function. Then, for every probability distribution P, any H in H, and every sample size m and every delta we have that the probability over S coming from P to the N that there exists H in H for which L S of H minus LP of H is greater than epsilon n is less than delta, where epsilon n is Okay. This should be n of h, and I need n of h is the minimum over all n such that h belongs to hn, and epsilon n is the minimum epsilon n of epsilon n is the minimum epsilon such that m is greater than m. This is becoming crazily unreadable, right? This is, I'm just realizing as I'm writing it that if I'm losing myself, I'm definitely using you as well. Okay, let me write it down. It all appears is the minimum epsilon n is the minimum epsilon such that m suffices to learn with epsilon with probability w of n times delta. Okay, so let me just try to explain it. I realize that it's becoming impossible to follow. But let me explain what is happening here. So the trick is that now I ask the difference. Usually what we will want to do is we will want to make sure that the difference between the estimate and the true loss is not more than epsilon. But now I allow this epsilon to change with the complexity of h. So what is this epsilon allowed to depend on? This epsilon, first of all, I'm asking where is h coming from? The higher the level h is coming from, the more strict my requirement is going to be. So I'm asking, so n of h is the class hn for which h came. And now epsilon n is, I'm asking, I mean, we are giving some sample size. I'm asking with this sample size, to what precision can I learn the class hn? I'm kind of reversing. Before, we had epsilon and delta, and we computed m of epsilon delta. Now I'm giving m, and I ask, I'll fix my delta, and I'll ask, what epsilon can I tolerate? If this is my sample size, what is the minimum epsilon such that this sample size will still suffice? So I'm picking the minimum epsilon such that my sample size that I have here still suffices to learn the class hn with this confidence. I really don't know how to dig myself out of this hole in terms of communicating. I don't want to just talk to myself. So, okay. This is the theorem that I need that replaces the claim that we have epsilon delta learnability. Here we have for the probability that I will miss by a function that depends on where h came from is bounded by delta. And the function that depends on where h came from is this kind of complicated function, the minimum m that I need to learn with precision epsilon. I think I will just leave the proof in this statement, and rather than proving it, show you what is the algorithm that results. So, or maybe, I don't know, maybe proving it will be useful. Okay, so let's do here a proof idea. So it has two steps. Step one, we have to see that for every n, the probability and every m, the probability for s coming from p to the m, that there exists an h in Hn such that Ls of h minus Lp of h is greater than epsilon n is less than delta, is less than delta times Wn. So this claim, okay, why is this claim true? This claim is just true by our choice of epsilon n. You see, epsilon n was chosen in such a way that with this sample size, I can achieve this epsilon n for delta equals Wn times the original delta. So I picked epsilon to be large enough such that I can achieve this with probability delta times Wn. Delta times Wn is just a fraction of delta. And that was encapsulated in our definition of epsilon n. Epsilon n was the minimal value of epsilon that can tolerate such confidence with m size sample. And now step two will say, this is, you see, step one talked about a specific Hn. This is for every h in Hn. This talked about a specific Hn. Now if I want to say something for every h in H, I have to take the union over all Hns. So to take for every h in H, yes? Yeah, it's the absolute value. Thank you. Right. So the only step that is missing is the union bound over all n's. For every particular Hn, we have this claim due to our choice of epsilon n. So if I want to know what is the probability over S coming from Pn that there exists an H in the union of all the Hns such that the same thing happens, Ls of H minus Lp of H is greater than epsilon n. If I want to estimate this probability using the union bound, so let me just continue here with the union bound, it is going to be less or equal than the sum over all n of the probability that this will fail for Hn. So it's the sum over all n of delta times Wn. For every class Hn, this is the probability of failure. So the probability that one of them will fail by the union bound is at most the sum of all of those probabilities of failure. But what is this number? Right, it is delta times the sum of Wn, which is just 1, which is at most delta. So by this tricky choice of epsilon n, we got this convergence over all members of H. Okay, so we proved this. What we'll do next time is describe the algorithm that does this learnability. Thank you, and sorry for the combat sum notation. It's all in the book if you want to go over it.